Welcome back to ECE 320A. And today what we want to talk about is Laplace transforms. And this is now chapter 12. What we want to do is we want to move beyond sinusoidal steady state. We want to be able to do something more than always worrying about shaking at a fixed frequency. We want to be able to worry about transient behavior. We want to worry about multiple frequencies in one solution or as we analyze these circuit problems. The way that we are going to enhance our ability is by learning about the Laplace transform and using Laplace transforms to analyze electric circuit problems. Have you seen the Laplace transform before? In your differential equations class? No? Where have you seen it? If it wasn't in different... What?
Right there.
Oh, right there, chapter 12. You're playing with me now. All right, so if you have you seen Laplace transforms before today? And if you have, it's probably in a differential equations class. It's the way that we will now basically convert differential equation problems into algebra problems. Everybody would prefer to just solve algebra instead of differential equations. That's how we will be using the Laplace transform. Today what we want to do then is talk about the definition of the Laplace transform and work through some examples with particular signals. I'll give you a waveform or a signal and ask, what does it look like, or what's its Laplace transform? And we'll start with very basic signals so that you have a feel for, oh, what's this look like in the time domain? When we talk about the Laplace transform, we are now actually moving into the frequency domain. Now we're in the frequency domain. Oh, I'm making you uncomfortable. I'm standing right next to you. So we will move away, but now when I talk about the time domain, I always kind of make a joke, but you might say, oh, I'm in the living room, I'm in the time domain. You might then go to the kitchen and say, now I'm in the frequency domain. So that you can make this connection between the two domains, you say, well, I've got this circuit problem and it looks like, okay, I've got R's, L's, and C's, and I've written the differential equations. I don't want to solve differential equations. I'm going to the kitchen. So you go into the kitchen and you work it in the frequency domain with Laplace, and now you simply do algebra. So I like the kitchen pretty well. Anyway, good things happen in the kitchen. You get to eat. So if we have time, we'll go through some examples of that where we will Laplace transform a differential equation, and we'll say, I'll give you another quiz. I'll say, can you find the differential equation of an electric circuit? We just want to start expanding our capabilities. Okay? So here's what we have. And I'm just going to kind of scroll through this at first, and then we'll slow down. The Laplace transforms are meant to be a simplifying transformation. That's why we want to go from the living room to the kitchen. We want it to be simpler. We want to not have to worry about all these differential equations that might be coupled. Now we just have coupled algebra to worry about. And these algebra problems will have S variables floating around. And what is S? S is a complex number. That's why Dr. Marcelin kept telling you we need to learn complex numbers. You need to be comfortable working with complex numbers. Now we're going to play with them a lot, and you need to be comfortable with them because now we can move from the time domain differential equations into frequency domain algebraic equations. From the living room to the kitchen. We want to be able to work back and forth between these two different domains. Time domain and frequency domain. That's what they pay you for when you come out and you say, I'm an electrical and computer engineer, and they'll go, Wow. You know how to work in both domains. Time domain and frequency domain. You now want to be able to do that. So here's the definition. If somebody hands you a time domain waveform f of t, and we're dealing with this in the single-sided case. We are looking at this f of t. We've now drawn a line in the sand. We've identified where t equals 0 is, and we say, what's this waveform from t equals 0 all the way up to infinity? And what does this do? Well, this says f of t is a time domain waveform. Some weird waveform, maybe. It may be an exponential. It may be a unit step. It may be an exponentially damped sine wave, an exponentially damped cosine waveform. Those are common signals. Those are common f of t's that we will play with. What do we do? Well, to find its frequency domain representation, it's capital F of s, and sometimes I'll get even more silly and I'll say we'll hit the shift key. You're having an f of t lowercase, that's in the time domain. You hit the shift key and you now have it in the Laplace in the frequency domain. You capitalize f. But what is involved in that process? What you do is you have this time domain waveform f of t for all time, from 0 to infinity. You scale it by this complex exponential. I said s was a complex number. So now s is a complex number. That's in an entire two-dimensional plane. But you're using that, it's now e to the minus st. T is still time. So you scale this f of t at each time by a frequency, a complex exponential, and then you integrate that information over all time. And what does that do? That boils all of that time domain information in that waveform down to a expression involving s. And that s is a complex number. It tells you a lot. It tells you the frequency information of a signal. That expression f of s. And the notation that we will use might be this. I might say script of a function, f of t, script of g of t. That's really just capital F of s. That I'm saying is the Laplace transform of that waveform or of that signal. So let's do one for a very simple signal. Let's look at the Laplace transform of the unit step. And everybody should be comfortable with the unit step. What is that? You shouldn't be sitting on the front row if you're asking, what is the unit step? Or if you are, you should be wearing shin guards, because I might kick you in the shin. But we all know, even before we go from the living room to the kitchen, we know what the unit step is, right? That's a waveform that's 1 for all non-negative time. It starts at 0, and it goes, and it's just 1 for all time. That's the unit step. It's a constant. So if I said, oh, you have a constant of 6, well, that's just 6 times the unit step. So if you know how to Laplace transform the unit step, you know the Laplace transform of 6, which is a constant. So let's see what this looks like as a capital U of S. What does this look like in the kitchen? What's the Laplace transform of this unit step? Well, we have the formula. And this is why, one of the reasons you took some calculus. You learned integration. But one nice thing is once you've seen these or learned these, you can just put them in a table. And now you have a table of time domain waveforms and their corresponding Laplace transforms already worked out. And if you need the Laplace transform of this function, you look in the table and you go, here's its f of s, here's its capital F of s, here's its Laplace transform. Let's derive one of those table entries. which is the Laplace transform of a unit step. So here it is. Script L of u of t is equal to capital U of s. And what did we say that was? Well, we said that that was the integral from t equals 0 minus. Is it okay what that 0 minus is? That just means the leftmost side of 0. Meaning, if this is splitting hairs, this is splitting epsilons, but this says that we're picking up everything at time t equals 0. We've gone just a little to the left of 0, and we're including everything that happens at 0 when we're starting at 0 minus. That's really all we're doing, is we're saying go from 0 all the way up to infinity. That's where we're integrating. And then we're integrating this function of time, u of t, which is right there. It's just 1 from 0 all the way up to infinity. But we weight that with this complex exponential, e to the minus st, and we're integrating time away. So now we have our formula for the Laplace transform of a unit step. And to do this, we plug in the time domain formula for the unit step. What is u of t as a function of time? 1. That's pretty easy, I hope. There's 1. We weight that with this complex exponential e to the minus st dt. Now we just have to integrate an exponential. E to the u. You probably learned that pretty early on in your calculus in the second semester if you get integral calculus in your second semester. So now you just have to integrate e to the u. But now u is actually a function of t, but you can do a variable substitution if you want. But I hope if this doesn't look right, you can go home and convince yourself this now will actually be minus 1 over s e to the minus st. Does that look right? Evaluated at t equals 0 minus and infinity. We're simply using the formula to find the Laplace transform of a unit step. We now evaluate that expression for the upper limit and the lower limit as a function of t. Or this is now minus 1 over s. That factor doesn't depend on t, so let's just factor it out. And we now have e to the minus s infinity, that's the upper limit evaluated, minus e to the minus s at 0. 0 minus, it's the same, it's 0. And do we know anything about these values? So this one vanishes, does it not? E to the minus a big number, that's gone. And e to the 0, that's 1. Now what we can't do is lose track of all of these negative signs. We have a negative of a negative. We have minus 1 over s times 0 minus 1. That just changes the sign of that 1 over s. Or we now have, this is minus 1 over s. Let me just go ahead and put it down. And what was that? That was the Laplace transform of a unit step. And you should see that in all of these tables for a one-sided Laplace transform. You give a unit step, a constant, that looks like 1 over s in the frequency domain. In the kitchen, that looks like 1 over s. So if you now had a constant voltage being applied to a circuit, you could say, oh, in the frequency domain, that's the constant divided by s. That contains all of the frequency information in that constant waveform, in that constant signal. Let's now, that was such fun, let's look at something else. Suppose now that we do something really challenging, we delay that step. Suppose we now say, what's the Laplace transform of a delayed step? So now I'm saying u of t minus t sub 0, where t sub 0 is some non-negative value. What does u of t minus t sub 0 look like? What's its value when it's non-zero? When it's non-zero, what's the magnitude or value of u of t minus t 0? When it's non-zero, what's its magnitude? It's 1, right? When it's non-zero. There's my, well, I probably shouldn't have done that before I write down what it is. But here is, whoops. There's a delayed unit step, is it not? And this is t sub 0. Meaning, the way to figure out when this is on and when it's off is to say, when is the argument of that unit step non-negative? Well, that tells us, if we say when is t minus t sub 0 greater than or equal to 0, that tells us that that's true when t is greater than or equal to t naught. Now, if somebody says, what's u of t minus t naught look like? You go, well, I need to find t naught on my time axis. And whenever t is bigger than that, that's when my unit step is active. It's when the argument of that unit step is non-zero. Or I should say non-negative. Okay, when is it roughly positive? Well, that's when t minus t naught, the argument of that unit step, is greater than or equal to 0. You solve that for t, which isn't hard, and now you say, oh, if t naught was 4, then when t is 5, you know that unit step is on. When t is 5,000, you know that unit step is on. Is that clear? That's a delayed unit step. Let's now find the Z-tran. My other class we're doing Z-transforms. So if you wanted to go into a different room, you could go into another frequency domain, which is the Z domain. We won't do that here. So correct me if I start slipping into different rooms. We're going to be in the living room and the kitchen, the time domain, and the frequency domain, which in this case is the S domain, Laplace transforms. Let's now find the Laplace transform of a delayed unit step. Again, if you're looking for partial credit, you could just write down the definition. And you say, oh, well, I'm trying to find the Laplace transform of this waveform, u of t minus t naught. And that is now scaled or weighted by this complex exponential, and I'm integrating time away. And you're going, oh, this makes my head hurt. I don't know what to do with u with that weird argument in the integral. If it was just u of tau, I'd be good, because I know that that starts at tau equal to 0 and it's 1 thereafter. Well, then let's just do that. Let's just tell it. Just make our life a little easier. What if we say, let's define tau to be t minus t sub 0? We'll teach it a thing or two. So now we have now converted this to work with u of tau, because that's what we feel comfortable with. We've learned how to work with that's Laplace transform. But if that's the case, now anywhere we see a t, we're going to have to change it, aren't we? So t now is tau plus t sub 0. And we're integrating from t equals 0 minus. What's that mean tau is going to be? If t is 0 minus, what is tau? If tau plus t0 is t. Isn't it just minus t0? If we have t equal to 0, then tau plus t0 is 0. Tau must be minus t0. What if t, which is the upper limit, is infinity? I really should say t approaches infinity because infinity doesn't exist, but we're going there, so I'm just going to be crude and say t is equal to infinity. What's tau when t is equal to infinity? It's still infinity. So tau is also infinity. Now we found our lower and upper limits of integration in this change of variable. And if we're using this, what is variable and what is fixed? T was variable. That was our dependent variable. That was our original variable of integration. What was t naught? That was a fixed delay, wasn't it? But tau is variable. So now I can say that d tau is equal to dt. A small variation in tau is the same small variation in t. So d tau is the same as dt. And now I'm ready to start doing this variable substitution in my Laplace transform definition for this delayed unit step. I now have that the Laplace of a delayed unit step is this integral from tau equaling minus t sub 0 to infinity of u of tau e to the minus s. Well, it was t, but everywhere we have a t, we replace it with tau plus t sub 0 d tau. And now we're going to use our knowledge of exponentials and say, well, I can rewrite this as e to the minus s tau times e to the minus s t naught. Right? And what do we know about e to the minus s t naught as a function of tau? It's not a function of tau, so we can pull it out of the integral. So now we've rewritten this as e to the minus s t naught integral from tau equal minus t naught to infinity u of tau e to the minus s tau d tau. Boy, that argument's looking really good because we just integrated something like that, but boy, those limits look a little different, don't they? We did have it from 0 to infinity. Now we have it from minus t sub 0 to infinity. But the integration operation is linear. We can just separate it into two integrals. Let's do that. So now we can say that this is the same as e to the minus s t naught from integral tau equal minus t naught up to 0 of u of tau e to the minus s tau d tau plus the integral from 0 to infinity, this is with tau, of u of tau e to the minus s tau d tau. But what's u of tau from tau equal minus t sub 0 up to 0? 0. It's not turned on yet, is it? We need the argument of our unit step to be non-negative to have a non-zero value. So this argument in the first integral is 0. This argument is 1, but we've already integrated that before. So that now we have the integral, e to the minus st0, 0 plus, this was 1 over s from before. Or this is now e to the minus st sub 0 over s, and that was the Laplace transform of a delayed unit step. So now we've just scaled 1 over s by e to the minus st naught, which was t naught was the amount of delay. In general, this holds for any delayed waveform that we already have a Laplace transform for. So let me just conclude, in general, the Laplace transform of a delayed waveform f of t is going to be e to the minus st naught Laplace of the original waveform f of t. Or this is now e to the minus st naught, capital F of s. And we'll start there the next time we're together. Thank you for waiting this out just a little bit longer. But that's now what we can do with a delayed waveform.